The node at the Universidad Autónoma de Madrid, led by Fernando Martín and Alicia Palacios, presents two main projects within the European QU-ATTO network. Our group has been working together for almost 2 decades to build up a solid toolbox to describe molecular ionization processes induced by ultra-short pulses. We've been able to predict and reproduce images of electron dynamics coupled with the nuclear motion in targets ranging from the simplest hydrogen molecule to targets as complex as amino acids, the building blocks of nature. To do so, time-resolved data on the scale at which the electron moves is required, that's to say, the attosecond resolution. Fortunately, nowadays, laser technology offers this time resolution. Our baseline is the solution of the time-dependent Schrödinger equation accounting for all electronic and nuclear degrees of freedom to describe the emission of one or more electrons, while keeping an accurate description of all electron-electron and electron-nuclear interaction terms. We combine scattering theory formalisms to ensure a proper description of the electron in the continua and of the emitted photoelectron in the presence of the remaining cation. An accurate representation of such interaction is critical in attosecond science, and it is one of the main goals of Project 1, identifying new strategies for controlling entanglement and decoherence in photoionization. This project is led by Professor Fernando Martín at the Universidad Autónoma de Madrid and Mark Vrakin at the Max Born Institute. The main objective is to estimate the degree of entanglement in photoionization and photodissociation of diatomic molecules. Recent experiments performed by the Berlin group demonstrated the possibility of controlling these quantities on the attosecond timescale in molecular photoionization, specifically in hydrogen. This study shows that the entanglement established in the ion photoelectron pair produced upon photoionization influences the emergence of electronic coherence in the dissociating molecule. More importantly, it was shown that a high degree of control over entanglement can be achieved by varying the delay between the attosecond pulses and/or the delay between those and the assisting few-cycle near-infrared pulse. One of the main goals of the project is the identification and optimization of these control buttons, and to do so, the Madrid group will use, among others, one of its most recently developed tools, the XChem package. XChem is a solution for an all-electron ab initio calculation of the electronic continuum of molecular systems, combining the tools of quantum chemistry and scattering theory to accurately account for electron correlation in the single ionization continuum of atoms and small and medium-sized molecules. The XChem package has provided reliable predictions for single molecule imaging or coherent attosecond control of chemical reactions. We now aim to apply this methodology to explore these novel strategies for the manipulation of photoion and photoelectron entanglement with attosecond resolution. The second project is led by Professor Alicia Palacios and focuses on attosecond pulse shaping to address novel attosecond metrology approaches. Her group has developed 4-dimensional methods to describe the single and double ionization of atoms and small molecules with incomparable accuracy. These tools will be used to tackle 2 sub-projects involving experiments with seeded free electron lasers at Fermi and intense high-order harmonics production at Lund University. The Fermi experiments will investigate coherent control schemes in doubly excited states of helium by accessing non-linear phenomena where electron correlation is the main drive of the observed dynamics. Such effects have already been shown in 2-photon absorption, leading to ionization in the vicinity of dark, double-excited states where strong variations of the specific angle of emission can be found, to the point that electron ejection in the direction of light polarization can be fully suppressed and an unexpectedly large electron emission can appear in the perpendicular plane with respect to the light. Even more interesting features were found upon the emission of 2 electrons, since the high correlation among the particles further shows dependencies upon light pulse duration. Experiments led by Professor Johan Moritzson at Lund University using intense high-order harmonic sources are planned to investigate new attosecond waveforms to control electron dynamics. First, laser-induced Rabi oscillations at the attosecond timescale will be explored. Pioneer theoretical works by the Madrid group demonstrated a stepladder-type mechanism occurring in molecules when Rabi oscillations are induced with intense fields among vibronic states. These strong field phenomena are now within experimental reach. Moreover, modifying the carrier phase is expected to lead to strong effects in ultrafast coupled electronic nuclear dynamics, even in the extreme ultraviolet range. This has been theoretically proven in small molecules, where the introduction of a pulse chirp allows higher frequencies to hit the target later than lower ones, or vice versa, as well as to significantly alter the outcome of the reaction. The present project will not only contribute to building up prior knowledge, but will also use the most advanced laser technology to examine the coherent control of strong field effects in the extreme ultraviolet range. Our PhD students in Madrid will closely interact with the experimental groups included in the network and benefit from training activities planned within our QU-ATTO network to foster the development of common scientific and transferable skills.